So, as the introduction, already done. So the goal of my talk is to introduce a couple of libraries that QFPL has produced for doing some graphics. And also, as Ken was saying, Haskell is normally associated with a lot of things like language research, back-end services, number crunching, DSLs for anything and everything, but not necessarily graphics and animation. So hopefully I can convince you otherwise today, as well as encourage and inspire a few of you, or all of you, or at least some of you, any of you, to try this for yourself. Because I profess no real expertise to what I was doing here. I learned a lot of it as I was going along. And by definition, generative and evolutionary art is exploratory. So just a quick definition, a quick cover of what this actually is if you've not heard of this before. Generative and evolutionary art is predominantly computer generated. They use typically some sort of repetitive algorithm, which is influenced by either just randomness or external inputs. And it is an intensely fascinating rabbit hole to fall down. There's many different variations on what actually constitutes generative art. It can be something like this, which is the substrate, or called the substrate artwork. It can look familiar. This looks a little bit like a city map, streets and different block sizes and things like that. But this was all algorithmically generated. Walk along a line until something happens, change direction, color it a bit, keep going. They can also be completely bizarre, but actually have some a strong mathematical underpinning. This one is using a technique called point advection, which, if I understand and remember correctly, is the maths behind animating fluids in 3D space. So that combined with a little bit of experimentation and sometimes an unexpectedly broken algorithm that produces something quite nice will give you these sorts of results. Or alternatively, it could be something really quite simple, but still have a very nice effect. And we'll actually cover off some of this particular example in the talk. So, why Haskell? Mostly types. Cool types, clever types, silly types, types of Clement rocks. But you also get other nice things that a lot of us enjoy in the world of FP, such as functions as values, delicious things like lenses, but also GHC, the Glasgow Haskell compiler, and GHC.js, the same but for producing JavaScript, are incredible pieces of technology that allow you to describe things at a very high level and get just exemplary performance and other benefits on the apps on the other side. Plus the traverse function. It's just a personal favorite. I love that function. I'll be using Reflex to power some of these examples. Reflex is a package and becoming a small ecosystem in Haskell for functional reactive programming. That is describing events and just behaviors of your application over time. And Reflex is currently one of the most advanced and capable examples of this. But it is also an incredibly deep topic, relatively easy to get into initially, but just like the generative art, a hell of a rabbit hole. So I won't have time to go into too much detail today, but there is a workshop happening here tomorrow, so sign up for that outside. It's awesome. And there'll also be some references at the end of the talk. But just so we're not completely flying blind, I'll just cover up a few of the basics. So within FRP, you can have this thing called an event. An event is just a value at a point in time. a button was pressed, the mouse was clicked. That's an event. It just exists at the time it happened, and then that's it. There's also this concept called the behaviour. The behaviour has a value at all points in time. As an example, how many times has the left mouse button been clicked? It may start at 0, and it exists as 0 for the rest of time until the button's clicked, and then it becomes 1. And then it's 1 for the rest of time. And you're able to interact between events and behaviours to get very complex, or take what will be very complex constructions or applications, and just tease them apart into their various components. Another aspect is this thing called the dynamic. The dynamic is unique to Reflex. So far as I know, it is a combination of an event and a behaviour. It allows them to perform some nice performance enhancements underneath the hood as things go along, but it also has some convenience when you're actually working with the code. Plus, there's a set of primitives that come with FRP for creating events, changing behaviours, creating behaviours. And it leans heavily on all of our good friends, the existing abstractions, functors, applicatives, monads, plus a few of their own, to get very predictable and reliable behaviour. So we'll just start talking about the first one. It's the tiled lines. So this uses the canvas on the front end, HTML canvas. And the basic idea of how to get the same effect: draw a line, decide if you're going to turn left or right, draw another line, do it again, and again, and again. So that basically will do the image we saw before. How do we draw a line? Let's have a look. So in JavaScript, you'd have to just be calling all of these different functions on the actual canvas itself after you've created it. And previously, you would have to write a lot of FFI code or manual integration with a lot of the JavaScript. But courtesy to an immense amount of work that's been done by the community and other interested parties, there's a collection of packages, one of which is ghcjs-dom, which packages up almost the entire collection of web APIs that are available in modern browsers. So we don't have to write any of the FFI calls ourselves. These functions exist as Haskell functions, just normal Haskell functions that we can use. So our Haskell code looks like that. It's not bad, really. The only real change is that context thing just moves to an input as opposed to whatever that weird OR thing is. So we'll just cover off what actually the context is. So whenever you're actually going to draw something with the canvas on the browser, you first need to put the canvas on the page, perhaps unsurprisingly. So reflex-dom provides a couple of nice functions for doing this. So there's a function called div class, which creates a div with that class. And then we can put an element inside that. We use that with weirdly named elatra function because we're creating an element that reflex-dom doesn't know about. So it doesn't know about the canvas tag specifically. So we tell it that we want this particular tag, we give it some attributes, and it doesn't have, that blank means it doesn't have any children. There's nothing that goes inside a canvas element. And then we use one of the new packages, reflex-dom canvas, to then request the context, to do some of the heavy lifting and to make it nice and convenient to use. So we pass in some config, which is this config here. We just give it the canvas element itself, and it does the work to go and get that canvas object for us. And the reason it returns a dynamic is because we have to use that same canvas context for any drawing or any changes that we're going to do on that particular canvas. And that canvas context is a terrifyingly large, scary, mutable ball of stuff. It has information. We can either give it instructions, we can ask it questions, we can put information in, get information out, usual things, but it changes over time, and we'd like to represent that in the most sensible way in the application, and in a way that's the most convenient as well. So we put it in a dynamic to indicate that it's basically, you have this value, it will change over time, you can run functions on it, trigger events, that sort of thing. And if that works, you've got the canvas info at the other side, which is just a record that has some information on it, like the element we actually put in, plus the context, which is the thing we'll be interested in. And then at some point, we've got to decide how we're going to turn, are we going to turn left, or are we going to turn right? So we need some way of defining randomness in our application. And this is where the fact that we get to use GHCJS is so awesome, because this means we have access to effectively all the package. If you have a particular flavor of random package on package that you like, good chance you're going to be able to use it. But how would we define left or right? Do we go 0? Do we go 1? Do we go either? True or false? It's Haskell. You just make another type. It's lazy. More types. It's always better. So we go left or right to left. And just some examples of how, like the flexibility you have courtesy of GHCJS and the fact that it's Haskell for getting some randomness into your application. So the first one uses I/O, which is basically calling out to, after it's compiled through GHCJS, that just uses the random function in the browser. We could manually pass in a seed, which is our standard gen there. And then when we execute this random function, we'll actually get the result, but we'll also get a new random seed. So this allows us precise control over just which parts we want to be consistently random or differently random as we go along. And again, you're also able to do the same function, but just calling out to the normal, like calling out to the JavaScript random without bothering to pass around or maintain your own random seed. And we have to do it a lot. Draw a line, turn a bit, draw a line, turn a bit. So the example I pulled from had this wonderful 4 runes. I'm not sure when they were last used. But they're effective. We could just cheese off that, do the Haskell version. But then we actually need, we've got all the pieces. So we've got the canvas instructions for drawing a line. We know how to turn left or right, or let something else work out which way we're turning. And we know how to do it a lot. So now we actually need to tell the canvas, run these instructions. And that's where a function from reflex-dom comes in handy. So we pass it in an event which contains a function, which is that JSMA, which stands for effectively JavaScript monad. And when that event fires, there will be a function inside, which is our drawing function. It is then up to the machinery inside Reflex to then execute that on the browser. So it's not our problem. It will execute it on the next animation frame or the next cycle, but it will only trigger that when we tell it to based on our event. So we construct an event for that to happen. In this case, we're waiting for the page to load. So we've just got an event, which is basically, after everything's been built, fire off an event. And our draw steps function will be the thing that actually runs against the canvas, but it needs the context, which we were storing in the dynamic from earlier. But that's okay, because they're leaning on all of the abstractions we know and love, so we can just fmap it in. And the current on the next slide, on the next section, basically turns our dynamic into the behaviour, just gets the behaviour out, and the weird left angle bracket at thing is a sampling action. So we could fmap this function over the context and have a dynamic of our function. That function will just be the same for all time. We use the event to sample that behaviour at the time that we want it, or at the time the event fires, rather. So that means we get So that's basically the result of that. But we can start firing events. Is that not working? There we go. So we can actually change. In this, we're changing the size of the steps. So we're changing the length of our line. And due to the algorithm, that changes the output that we get. So even though the algorithm itself is fixed, we can start messing with it. We can start arbitrarily adding inputs and then adding them to our functions. So we can change things over time. Just see what happens. Just add a quadratic curve. But thankfully, adding, courtesy of the structure of reflex-dom and reflex and the functions they provide, adding these extra inputs is quite straightforward. So we create a number input, which is that step size from the example, and we get, that provides us with a dynamic of the text input of that field. So we then have that step size value has the input field has a value for all points in time. And whenever we can choose to sample this at particular moments, so we can have a dynamic of all the step size that we're going to use, and then based on some event, in this case our buttons, which is just button was clicked, nothing, nothing, button was clicked. We can then sample the step size that we want to use. And then, based on that, we can then decide to increment or decrement the number of steps. So we can turn that into a dynamic of a function that we then basically just fold over time. That's just, so the inputs from our, where is it going? All right, so the input from the dynamic is just a text value. So we need to turn that into a number, obviously, for us to be able to use it in our example. So we're still just in Haskell, so we can just use read maybe, and we're good. So wiring it in, compared to what we had last time, the only difference now is we're fmapping, because our draw steps will now take the step size as an input to itself, and then we just fmap over that, so we've got the step size. Now we have a dynamic of functions, And the last thing we need to do is add the context, which, just as before, we use apply, and we get a JSM function, and now we combine the events that we've got. So initially, we'll do it once when the page is loaded, and then we use a combination of whenever one of those buttons is clicked to also fire this event, which will trigger the drawing. A lot less time than I anticipated. One of the other examples, which I won't have time to go through, unfortunately, was working with SVGs as well. So the packages also support working with SVGs on the front end as well as the canvas. Because previously, a lot of the, if you had to create the elements yourself, they would all be very stringly based. So you'd be typing in, you want to rect, and all of the different properties would all be text-based. So we provide libraries for working with data structures on all of those. There's also a WebGL example, WebGL integration. This was interesting because we stepped back from, with this particular example, it's not so much a matter of directly orchestrating the drawing actions, so drawing the individual lines on the screen. In the case of WebGL, those programs are separate. They run on the GPU. We don't control them. But you can still use Reflex to orchestrate those drawing actions based on the same events and behaviors. So, to sum up, it works. So you can use Haskell for graphics in the front end. It totally works. You can even use all of the existing MDN documentation from the Mozilla Developer Network. The same functions, they're just in Haskell now. But you also get to use Hackage and a lot of the nice things that come from there, like the linear package for doing linear algebra, when you're working with projection matrices, rotations, and that sort of thing for WebGL. There's Clay for messing with CSS. And there's also just the color package, which I found just very useful for doing all of the RGBA, HSL related computations correctly. It knew what it was doing, I didn't. It was very useful. Not everything was awesome though. Within the documentation that all of these API functions are generated from, some of the types that they list in there are just sort of notes, addendums. They don't actually exist anywhere. I lost half a day trying to create an array buffer view before I realized that it doesn't actually exist. It's just a helper type that's not a type. Some optional function arguments aren't. So this is the MDN, part of the snip of the MDN documentation for the fill function when you're doing 2D canvas work. You can optionally provide a fill rule or a path and a fill rule. But if we look at the Haskell type, that's not what we get to do. It says it maybe will take a canvas winding, a fill rule, but if you actually, and you expect that if you pass in nothing, it will just use the default. Nope, it doesn't, it crashes. But if you give it the default, it's fine. But this is hardly a failing of the API in general terms. There are thousands of functions and different layers of functionality to cope with, and it's all automatically generated. So this is a minor thing. So have a go. We've got, you can try anything. It's more than ready for, more than performant enough for games, within reason. We can start using SVG and Canvas for some charts on the front end, which is the boring aspect. That's why I was doing generative art, not charts. You could do your own art. And all of this is basically driven by the convenience and awesomeness of functional programming. And there's nothing to stop you now. Haskell on the front end, we're there. Let's do it. Thank you.
We'll take one question.
I don't know if that's a good thing.